Today, we're diving into a really cool story. It's about how a stubborn, thorny math problem, one that's been a real headache for researchers for years, was finally cracked. And the solution? It came from a clever technique borrowed straight from the world of AI. All right, so here's our game plan. We're going to start with the mystery at the heart of it all. Then we'll look at the old, kind of shaky way of trying to solve it. After that, we'll get into the new, elegant solution that's been a total game changer. And finally, we'll talk about why this whole thing is such a big deal.
So first things first, let's talk about the prize everyone's been chasing, a very special and very elusive number known as the L-invariant.
So what is this L-invariant anyway? Well, you can think of it like a secret key. You have these incredibly complex mathematical objects called elliptic curves. And the L-invariant is a number that helps unlock their deepest secrets. It's absolutely crucial for proving some of the biggest ideas in number theory.
And this really gets to the heart of the whole thing. It's not that mathematicians don't know what this number is. They've known about it for a long time. The real head-scratcher, the central challenge, has always been just figuring out a reliable way to actually calculate it.
Okay, so let's look at how people used to tackle this. And you're going to see pretty quickly why it was, well, let's just say it was fundamentally flawed. The classic approach is something called finite differences, and honestly, it's pretty intuitive. It's kind of like trying to measure how steep a hill is by taking one tiny step forward and seeing how much your height changed. Seems simple enough, right? But there's a hidden trap.
This reveals this huge paradox. That tiny step you take, what they call h, is the source of all the trouble. If you make it too big, your measurement is clumsy, you miss the details, and you get the wrong answer. But if you try to make it super small to be more accurate, your computer just can't handle the tiny numbers and starts making massive rounding errors. You're completely stuck between a rock and a hard place.
And boom, here's the visual proof. This is the V-curve of error. And it shows you plain as day that you just can't win. Whether your step size h is too big over on the left or way too small on the right, your error just shoots through the roof. There's no sweet spot. There's just no safe place to stand.
So if the old method is basically a dead end, what's the big breakthrough? Well, believe it or not, the answer comes from a field you probably hear about every day: artificial intelligence.
The new method is called automatic differentiation, or AD for short, and it's a totally different way of thinking. Instead of taking one big sloppy approximation at the very end of the calculation, AD is like having every single number carry its own little instruction manual for how it's changing, step by step. It tracks the exact rate of change all the way through, so no approximation is ever even needed.
And here's the really cool part. This isn't some brand new, untested idea from a lab somewhere. This is the exact same powerful, battle-tested engine that's used to train the massive AI models we all know about. Researchers just took this incredible tool and aimed it at this old-school pure math problem.
Okay, this brings us to the main event. How does this new method, this automatic differentiation, actually stack up against the old way in a head-to-head fight?
Let's just look at the raw data. The top row shows a pretty big step size, and yeah, the error is huge, no surprise. Now, look at that middle row. That's the old method's best shot. It gets really, really close. But then, look at what happens in the last row. When you try to get super precise and make h incredibly tiny, the whole thing just falls apart. The error doesn't shrink, it explodes. The method completely breaks down. And when you see it on a graph, the difference is it's stark. That perfectly flat, steady blue line at the bottom, that's the new method. Rock solid, stable, and exactly right. And that red line, that's the old way, perfectly tracing that V-curve of failure we talked about, collapsing no matter which way you go.
But hold on, because it's not just about being accurate. That's only half the story. The new method, that solid blue line, is also incredibly fast. This chart shows that as the problems get bigger and more complex, its runtime barely budges. It just scales beautifully. And to put a concrete number on that speed, they tested this on a seriously complex 800-dimensional problem, and it gave them the exact answer in, get this, less than 1/10 of a second. That is just astonishingly fast.
So, okay, we have a clear winner here, on every single front. But let's zoom out for a second. What does this all really mean for the bigger picture? Here are the key things to take away. We're replacing an unstable, error-prone guess with a method that is stable, precise, and lightning fast. But even more importantly, it shows that you can take these powerful tools from one field, like AI,
and use them to unlock completely new possibilities in another, like pure mathematics.
The conclusion from the paper just says it all perfectly. By thinking about the problem in a new way, not as an approximation but as a differentiable program, something a computer can track perfectly, we can solve it in a fundamentally better way.
And this leaves us with a final, really provocative thought. This whole approach worked because they decided to treat a classic math problem like it was a piece of computer code. And it makes you wonder, what other impossible challenges in science and math are out there, just waiting for someone to come along and look at them from a completely different angle?